Build my home on hollow ground. Too proud.
Hi, this is Craig Smith with a new podcast about artificial intelligence. This week, I talked to Yann LeCun, one of the brightest minds in machine learning today. His work lies behind some of the most critical AI applications, most notably computer vision systems that power everything from face recognition software to self-driving cars. Yann recently won the Turing Award, the highest prize in computer science and artificial intelligence research, together with his longtime collaborators Yoshua Bengio and Geoff Hinton. We talked about Yann's first computer, about how the oboe and other wind instruments led him into computer science, and about his work on self-supervised learning, which Yann believes will take us to human-level intelligence in machines. I hope you find the conversation as fascinating as I did.
Cross it to find your synthetic light.
You're French.
I'm French. French and American now, but yes. I was born near Paris. I grew up near Paris on the outskirts.
In the banlieue or?
Yeah. Not that close. Northwest, kind of Soisy-sous-Montmorency, Enghien-les-Bains, Aubonne. This is kind of this area. I was always interested in engineering, science, and things like this, and I was interested in, at the abstract level on the question of intelligence. How did human intelligence appear? What is intelligence really? So that's a question I was fascinated by since I was a kid, essentially. So that goes back a long time. I saw 2001: A Space Odyssey when I was 9 years old, and I thought the concept of an intelligent machine was amazing. And that movie also put together not just intelligent machines, but how some hypothesis about how human intelligence evolved, right?
Yeah.
So
that's right.
So that was all the topic I was fascinated by. What you see here in this room is that all this decoration. These are pictures from the 2001 movie.
Yeah.
So that's how I got interested in this question, and I always thought I could be a scientist or an engineer. My dad was an engineer, mechanical engineer. I studied engineering, electrical engineering. And I took a lot of courses in, applied math and physics and things that were kind of fairly fundamental. And I started doing projects in, I guess, what you could call AI, I guess. Mm-hmm. I got interested in neuroscience also.
This is all in high school, or this is now in college?
No, this is in college.
Yeah, and that was where?
That was at a school called ESIEE, which is not a huge top engineering school, a decent engineering school for electrical engineering in Paris. That school since moved to east of Paris, like near Disney, Euro Disney. Sure. But back then it was in Paris, in the 15th arrondissement. And I did a bunch of research projects with various professors on sort of, kind of computer models of neurons and stuff like that. And I discovered the existence of learning machines by reading a philosophy book, actually. It was a debate between Noam Chomsky, the linguist, and Jean Piaget, the developmental psychologist.
Sure. Yeah.
And they were arguing about the nature-nurture debate, right? And, is language acquired? Is it innate?
I just had a conversation with Ken Church, who was a student, about all of this. Yeah.
And he's a former colleague from Bell Labs, actually.
Oh, that's right. Yeah.
So... I read this thing, and there was one of the talks that was transcribed in that book was by Seymour Papert from MIT, where he was singing the praise of a model called the perceptron, which I had never heard of before, which is one of the early kind of simple learning models, right, from the 50s and 60s. So I read about this, and I said, a machine that's capable of learning, I find that absolutely fascinating. I always thought learning was indistinguishable or inseparable from intelligence, that you could not I thought the task of building an intelligent machine was impossible, but building a machine that could learn maybe was a possibility, right? So I started digging the entire literature. I must have been in maybe third year of college or something.
What year would that be?
That would be 1980, 1981.
Wow. Yeah.
And then discovered that nobody was actually working on this anymore. The entire field had been abandoned in the late 60s because of a book co-authored by the same guy, right? The Seymour Papert, who was,
was that the Minsky book?
The Minsky and Papert book.
I didn't realize he was the co-author. Yeah, Perceptron, right.
So that pretty much killed the field, or at least had a big impact on the field. And there it was, he was 10 years later actually kind of praising the perceptron. It's kind of interesting to argue against Chomsky's argument that language is innate. So I got interested in this, and I thought, why is it that people abandon this idea? It sounds like a really cool idea, and then realized very quickly that what people were kind of, the wall that people were hitting against at that time was that they knew that the perceptron in itself was very limited, and there was a need for being able to kind of build multi-layer neural nets.
Right.
And they knew that, they just didn't figure out how to do it.
Right.
And it's probably mostly because they had the wrong neurons. The neurons people were using in neural nets at the time were binary neurons.
Right.
And that's incompatible with things like backprop.
Right.
And so the idea didn't come up, even though the basic idea of doing backprop actually existed in the context of optimal control since the 60s. So, the whole field kind of died, or rather changed name, because instead of working on intelligent machines, the people working on the perceptron at the time and related models started renaming what they were doing. It was called adaptive filters and things like that, but it was the same thing really they were doing. And so I started thinking about, how can we train multi-layer networks, and kind of stumbled on an idea that, which was very close to backprop. So this must have been 1983 or so. Which was the idea of using the weights that are used in the neural net forward. You use them backwards. I wasn't using them to backpropagate gradient. I was using them to backpropagate targets. So basically to compute virtual targets for every neuron. My neurons were still binary. And the reason was the computers we had access to at the time were very slow at computing multiplications.
Right.
And so if you have binary neurons, you don't need to do multiplications. And then I talked to a friend of mine who was doing a PhD in control, in robotics, who told me about those methods that, in robotics that people had, or in optimal control that people had come up with in the 60s. And I said, that looks very much like the stuff I'm working on. And so that's when I kind of came up with backprop. But then a month later or so, or a couple months later, I met Jeff Hinton, who came to a meeting in France, and I really wanted to meet him because he had written a paper on Boltzmann machines, which I think was it was the first paper I saw that basically allowed to train neural nets that had hidden units, right? So I thought I want to talk to him, right? Either him or Terry Sinowski. I actually met Terry a couple of months earlier, and so I meet. Jeff at this meeting in France, and we start talking, and I tell him what I'm working on. I had a paper in the proceedings of the conference he came to that talked about this target prop idea, and he read it and he said that's really close to backprop. And so we talked together, and I told him what I was working on, which was backprop, and then he told me what he was working on, which was also backprop. And so, they just totally lined up. And he said, I'm writing a paper, and, I'm going to cite your paper in mine. I was absolutely delighted by it. And that's how I met him.
Was he as prominent then in the field?
He was somewhat, because of the Boltzmann machine paper, and it was just the beginning of the wave, or the second wave of neural nets. Right. This is mid-1985, so nobody knows about backprop yet, but Boltzmann machines have been around for a couple of years, and it was clear that there was, there's going to be a lot of people kind of trying to kind of restart, working on neural nets. He wasn't nearly as famous as he is now, of course, but he was kind of, fairly well known. So then he told me, I'm organizing a summer school next summer, 1 year later, and said, I'm going to invite you to that summer school, and we're going to bring together all the students who are working on neural nets and all that stuff. And that was sort of the founding event, if you want, of the sort of neural net community, really.
That was in California?
That was at Carnegie Mellon.
Oh, he was at Carnegie Mellon at that time.
That was in 1986, the one I'm talking about.
Okay.
So I was at Université Pierre et Marie Curie, which now has a different name now. It's called Sorbonne Université. But I actually didn't spend much time at that school because the person who was officially my advisor was a professor at that university, so that's where I was officially registered. But I was actually spending most of my time in two labs. One was at the engineering school where I did my undergrad, because that school happened to have fairly powerful computers for the time, which I could use, and also in an independent lab where my advisor spent some time, and a few other people who had kind of a common interest in what they called automata networks, which was sort of connected with neural nets, and these people kind of got involved in neural nets pretty quickly. So in 1987, I graduated. This is just when the backprop paper was had been published a year before. The NetTalk thing that Terry Sejnowski built. He kind of ran around and gave talks about this. All of a sudden, the people in France who had been basically ignoring me for years started talking to me because I was the local expert on those multi-layer nets, right? So I finished my PhD. Jeff was actually on my thesis committee, and then I did a postdoc. I started a postdoc with him in Toronto. So he moved to Toronto from CMU in the summer of 1987, and I arrived in Toronto 2 weeks after him.
I see.
So I was invited in the winter of 1987 to Montreal. I gave a talk there, and in the room was this kid who asked really smart questions about neural nets, and there were very, very few people working on neural nets at the time. That was Joshua. I kept an eye on him.
Was Sammy there by chance?
I didn't meet Sammy until 3 years later, I think.
Yeah, look, I just think it's fascinating. They're two brothers in this field, and then it turns out your brother works for...
He works at Google.
Yeah,
in Paris. Yeah, he's not working on machine learning.
But still, it's
operations research, optimization kind of person.
Yeah, what did your parents do that they have these two brilliant kids doing stuff?
Well, my mom was a homemaker. My dad was a mechanical engineer working in the aerospace industry. And he was kind of a bit of a mechanical genius. I mean, my brother and I learned everything from him, basically.
Oh, wonderful.
We were kids, we were like, build model airplanes and, electronics and stuff like that.
Yeah. What was your first computer?
Oh, my first computer I bought when I was still in high school. This was in 1977.
Yeah.
I'm sorry. So this was before you could buy a computer with a screen and a keyboard, right? This was a single board computer, which had, it was just a printed circuit board with a 6502 microprocessor, 1K of RAM, 4K of RAM or something, an hexadecimal, keyboard and LED display with 6 digits, the 7 segments, 6 digits. And you would program it directly in machine language, in hexadecimal.
Who was the maker?
It was a company called MOS Technologies.
So not...
Synatech, actually. The company that made the board was called Synertech. I don't know how you pronounce it.
Yeah.
It didn't last very long. But you basically had to know like how a microprocessor worked inside to be able to program those things. There was no, high-level language or BASIC or whatever, right? It was directly machine language to program into. And my main motivation for getting into this was two things. Long-term AI, whatever, but short-term music. I was into electronic music, not just electronic music in general, and I wanted to use computers for music, essentially.
And the music thing faded, or did you do it on the side?
It didn't fade, really. I have a bunch of analog synthesizers and various other things, and I build wind controller. I'm a wind instrument player. So,
like which instruments?
Like oboe recorder and various exotic Renaissance instruments. So, but I build wind controllers, so you can blow into them. It sort of figures out your fingering and there's sort of various controls and so there's a bunch that I just bought and there's a bunch that I built.
Wow, fascinating. Okay, so fast forward, then there was a moment when neural nets died again. largely because of insufficient hardware, I think. And then, and that was the point at which you, Jeffrey, that's why everyone talks about the three of you together, right? Didn't you come together and sort of revitalize the field?
It's slightly more complicated than that. So there was like a very favorable period in the late 80s, early 90s.
Mm-hmm.
So I joined Bell Labs in the late 80s. I hired Yoshua actually at Bell Labs. He worked there for a few years with us, the first half of the 90s. And other people like Léon Boutou and Patrice Simard. I mean, a bunch of, Vladimir Vapnik was in our group too. I mean, those are kind of big names in the community. And we became really successful with the techniques we developed, convolutional nets. We kind of were able to build systems that could read checks and zip codes and various other things, and the engineering divisions of the company actually commercialized that.
Yeah, I remember
that was quite successful. But just at the time that it started being successful commercially in 1995 roughly, two things happened. First, the machine learning community lost interest in neural nets. And the second thing is that AT&T, which
broke up.
owned Bell Labs, broke itself up.
Yeah.
For the second time.
Yeah.
And that was a bit difficult for me because when the company broke up, the research group where I was in stayed with AT&T, so that took the name AT&T Labs. The reason being that the guy in charge who became in charge of Bell Labs didn't like machine learning at all, so all the machine learning people went to AT&T. The engineering group was in Lucent Technologies, which was one of the spin-offs, and the product group was in NCR, which was yet another spin-off. And so the whole project was basically disbanded. So this was like my biggest technical success, as well as technology transfer success, and all of a sudden it was taken away from me almost on the same day that we were celebrating its deployment, essentially.
Yeah.
At the same time, I was promoted to department head, so now I had to also run a lab.
Yeah.
And this was the early days of the internet, so basically I kind of tried to figure out what I should do next. And for 6 years, essentially didn't work on machine learning at all. I wrote papers on stuff we did before, but I started a new project called DJVU, that was sort of a image compression technology that was somewhat successful at some point. And then ran the department until early 2002 when I left AT&T, and that's when I restarted working on machine learning, deep learning, etc. And that's just about when Yoshua, Jeff, and I kind of got together and sort of started the deep learning conspiracy, if you want.
Yeah. And where were you then when you left AT&T?
So I left AT&T, went to the NEC Research Institute in Princeton.
Right.
I stayed there for about 18 months. I brought a lot of people from my lab there, about four people, from 5 people actually, from my lab from AT&T. Léon Boutou and Vladimir Vapnik and Eric Kozato, Hans-Peter Graf, and a couple other people. And but then I only stayed 18 months because NEC basically was kind of in a very sort of complicated transition period, and they were not interested in all the people I wanted to work with at the NEC Research Institute were leaving. There were, physicists, neuroscientists, quantum physicists, and all the interesting people kind of started leaving. So I started looking for another gig, and that's when I joined NYU. That was in 2003.
Oh, is that right? I didn't realize you'd been here that long. Yeah. So a lot of the really important work has been done at NYU.
So I mean, a lot of the foundational work was done while I was in Toronto and Bell Labs in the late 80s, early 90s. And then I kind of started working on this at NEC, but really sort of the more recent work, was all done at NYU.
So can you talk about the importance of learning representations in neural nets? I mean, neural nets depend on representations, so that's the whole point.
All of AI relies on representations. The question is, where do those representations come from? So the classical way to build a pattern recognition system was to build what's called a feature extractor, which turns the input signal, whether it's an image or audio or whatever, into a representation, generally a vector, a list of numbers, that represent the salient features of the input that are useful for the task that you're trying to do, right? So if you're trying to do speech recognition, you want some representation that takes into account the nature of the sound that is being pronounced, but doesn't care about the identity of the speaker, for example, or the pitch of the voice, right? Unless it's Chinese. If you want to do speaker recognition, like figure out who is speaking, but you don't care about what is being spoken, then it's other features that you need to extract from the input. Same for images, right? If you want to recognize an object in the image, there are certain features that are probably useful to extract. But people had, for things like image recognition, people have been working on the problem of what are the right features for recognizing objects. And there was no real good way of extracting features that would be general for any recognition problem that you had. So there's a whole lot of papers on what features you should extract if you want to recognize handwritten digits, and other features you should extract if you want to recognize like a chair from a table or something, or detect them in images.
And that was just based on trial and error or intuition? Intuition,
engineering, a little bit of theory, but mostly, signal processing methods and stuff like that. In computer vision, that means edge detection, things like that. In audio processing for representing speech, for example, that means doing Fourier transform to extract the spectral content and then doing some operations on it. So every specialty had its own way of extracting features to represent the input signal.
Right.
And most people spend their entire career trying to figure out, what are good ways to extract features. So the idea of multi-layer neural nets is that you can think of the first few layers as extracting features for the following layers to use and classify if it's a classifier. And if you can train the entire thing end to end, that means the system learns its own features. You don't have to engineer the features anymore. They just emerge from the learning process. So that's what was really appealing to me, and the idea that there's necessarily some sort of hierarchical structure in those features. And the reason why you need some sort of hierarchy is because the perceptual world, like the natural data, is compositional, in the sense that pixels kind of assemble to form edges, for example, and edges assemble to form motifs like corners and crosses and things like this, or gratings. And then those motifs assemble to form kind of more complex shapes like circles and squares. And those assemble to form parts of objects, and those assemble to form objects, etc. So you have this sort of natural compositional hierarchy. And it's the same in speech. You have, raw signal, and then phonemes, words, sentences, etc. You have the same in text. Just about any natural language, you have this sort of compositional hierarchy, because the world is compositional.
And the visual cortex also has these layers.
That's right.
Is that right?
Yeah, so there's anatomical layers and these functional layers. So here we're talking about the functional layers, right? So the visual signal goes from your retina to a little piece of the brain at the bottom called LGN, and then it goes to the back of the brain, V1, V2, V4, IT, and IT, the inferotemporal cortex, is where objects are encoded, object categories are encoded. And some neurons will fire when you look at a chair, regardless of what chair it is, if it's occluded or not, if what type, what orientation, what color, it doesn't matter, right? So that's called invariant representation.
But there is a hierarchy of components, right? It starts. There are neurons that fire when it sees a cross or when it sees an edge,
right? And
then that gradually is built up.
So this is that's called the ventral pathway hierarchy, right? V1, V2, V4, IT. These are the four big, visual cortex areas that are used for kind of recognition of objects in the visual field. That's only 5 layers. There's more kind of internal layers if you want. And so the next question I asked myself very early on, before even I got to Toronto, when I was finishing my PhD, is can we build a network whose architecture would be somewhat inspired by what we know of the visual cortex? There was very classical work from the 60s by Hubel and Wiesel on the architecture of the visual cortex, right? Simple cells, complex cells, etc. It was a very natural idea, and which people already had in the 60s of connecting neurons to a small area in the visual field, so they detect local features and things like this, right? And I built neural nets like this, before even I came up with Backprop, that tried to kind of reproduce this kind of architecture with the crude software tools I had available. So what I set out to do when I got in Toronto was I'd started an ambitious project of writing a neural net simulator with Léon Bottou, whom I met just before I left France. And we started writing a neural net simulator together called SN, which turned out to be very instrumental in allowing us to do the experiments with early convolutional nets and things like this. You need, at the time you needed a lot of investment in software to be able to do those things. There was no MATLAB, there was no Python, there was no, you basically had to write everything yourself, right? We even had to write our own Lisp interpreter. So anyway, I get to Toronto. I work on this software. Léon writes on the, keeps working on this software on his side as well. And then finally I can try convolutional nets. And it's based on the idea that I was inspired by papers by Kunihiko Fukushima on the neurocognitron, where he had tried to kind of build also a model of the cortex using those simple cells, complex cell hierarchy idea. And this model was a little overly complicated. He was trying to stick to kind of the neuroscience and the biology, there's a lot of things to adjust in his model to make it work. It was a little Byzantine in many ways. He didn't have backprop, so he couldn't train it end to end. He had to come up with some sort of unsupervised learning algorithm for it. So what I set out to do was basically, build one of those kind of visual hierarchical model inspired by Hubel and Wiesel, but train it with backprop. That was convolutional nets. So this started working in the spring of 1988 when I was still in Toronto. Did some early experiment there, and then I moved to Bell Labs. And at Bell Labs, they had a big data set of 9,000 training samples of, zip code digits. And I tried it, my code was ready. I just tried it on the data set, and within 2 months, I had, better results than everybody else.
Wow. So neural nets learn the representations. You don't have to prepare the representations and then put them in as inputs.
Right. So because of this multi-layer structure, and in the case of convolutional nets, because of the local nature of those neurons, they only look at a small thing, then it exploits this compositional nature of natural signals, if you want.
Yeah.
And a lot of it was intuition. Some of it was a little bit of biological inspiration. Of course, the whole idea of convolution and pooling and things like this are very classical things in signal processing. Orthogonal to machine learning, right? And since then, there's been theoretical work that kind of show that this kind of architecture is a good idea for certain types of signals. You can prove it, okay? But back then, it was more kind of based on intuition. Yeah. There is a limit to what you can apply deep learning to today, due to the fact that you need a lot of labeled data to train them. And so it's only economically feasible when you can collect that data and you can actually label it properly. And that's only true for a relatively small number of applications. So that's one mode of training, right? Supervised learning. It works great for, categorizing objects in images, for translating from one language to another if you have lots of parallel text. It works great for speech recognition if you have collected enough data. But it doesn't work for all kinds of stuff. Like, it doesn't work for translating every language into every other language, because we don't have parallel text for every language, every pair of language. It's very important for Facebook. People use, thousands of languages on Facebook, and we don't have parallel data for every pair of language. It's very important also for a lot of areas where it's very expensive to collect data, like medical images, for example. You will never have enough data. And then there is a lot of situations where collecting data is just not the right thing, or is not sufficient. For example, if you want to train a system to hold a dialogue with someone. You cannot just collect a training set and train the system to hold a dialogue. You actually have to train it with people, like talking with people, right? If you want to train a system to interact with an environment, you have to have an environment in which it can train itself to interact. So that's one problem. The second problem is there is a second type of learning called reinforcement learning, which has gathered a lot of press lately because,
met Richard Sutton at Montreal.
So Richard Sutton is one of the founders of this area, and it's sort of a weaker form of learning in the sense that you can rely on instead of telling the system, here is the correct answer, you only tell the system you're right or you're wrong, or you give it a number that corresponds to how right or wrong you think it is. Mm-hmm. And that number can be generated automatically by the environment. So for example, you want to learn to ride a bike. If you fall, that's a negative reinforcement. If you keep riding the bike for another second, that's a small positive reward, if you want, right? So by trying to figure out the sequence of action that maximizes the reward, then maybe you'll learn to ride a bike. Here's the problem, though. Almost any human is capable of learning to drive a car in about 30 hours of training with hardly any supervision. If you were to use reinforcement learning, at least in its current form, to get a car to drive itself, it would have to crash thousands of times. Yeah. It would have to drive hundreds of thousands of hours, if not million. Yeah. Crash thousands of times, kill many pedestrians, destroy itself multiple times, run off cliffs multiple times before it figures out how not to do it. Yeah. And so what that tells you is that we're missing something really essential in human and animal learning that is not reflected in the type of reinforcement learning or supervised learning that our machines can do. Right? A kid can learn, the meaning of 10 new words per day, can figure out what an elephant is with just 2 pictures, right? And we can do this to some extent with learning today using transfer learning. You pre-train the machine with lots of images, and then you can retrain it to recognize new objects with very few samples. But there is something we're missing. Mm-hmm. And one hypothesis that I have, and Yoshua agrees, and Jeff has been saying this for 30 years or more, is that thing should be unsupervised learning, which means just learn how the world works, just learn the dependencies, the structure, the regularity of the world by observing it. So I have a form of it called self-supervised learning, which is a very natural idea. Imagine that you give the machine a piece of input. Let's imagine it's a video clip, for example. You mask a piece of the video clip and you ask the machine, pretend you don't know this, and try to predict what is masked from what you're seeing. So predict the future of this video clip, what's going to happen in that video from what you can see from the past. Mm-hmm. Or here is an image, I'm going to block a piece of it, like can you reconstruct that piece? In the context of text, you give it a window of, 1,000 words on a text, and you take out 20% of the words, and you ask the system, can you predict what words are missing? And so when the machine trains itself to do this kind of filling in the blanks, it has to develop some representation of the data so it can do this job. Yeah. So to be able to predict what's going to happen in a video, you kind of have to understand, that there are objects that move independently of backgrounds, and there are objects that are animate other than that are inanimate. The inanimate objects have predictable trajectories, the other ones don't. Yeah. Right. Things like that, right? And so presumably, by training a system to predict or filling in the blanks, it's going to have to understand a lot about the structure of the world. And so the idea is that you would train a system in this self-supervised manner with tons and tons of data. There's no limit to how many YouTube video you can make the machine watch. It will distill some representation of the world out of this. And then what you would do is whenever a particular task comes in, like learning to drive a car or recognizing particular objects, you use that representation as input to a classifier, and you train that classifier supervised. So that's the whole idea. And in fact, this is an idea that Jeff, Yoshua, and I actually started with when we got together to kind of restart to to start the deep learning conspiracy, around 2003, 2004. The idea was to use unsupervised learning to pre-train a network and then fine-tune it using supervised learning. Because we had this idea that it was very difficult and perhaps hopeless to train a very, very large, very deep network using backprop. It wouldn't work. So the idea was, we would pre-train it using those kind of unsupervised methods. And so Jeff worked on Boston machines, Joshua worked on Boston machines and using autoencoders and various other things, and I worked on sparse autoencoders. There's sort of various methods that we proposed to do this, until we realized with all the tweaks that we developed in the process, rectifying nonlinearities and draw pattern and things like that, that in fact you could train very deep, very large neural nets with backprop from scratch if you had GPUs. So the hope is that by training a system to, in this kind of way, the kind of representation that would be extracted will be sort of more complete, if you want, less degenerate than the kind of representations that are learned when you just train a machine to, for a particular task, right? When you train a machine for a particular task, it just learns the features that are useful for that particular task.
Right.
In fact, one thing that became clear pretty quickly was that the best way to train a convolutional net is not to train it to distinguish one class from another, like with two classes. Like, if you want to train a neural net to do, pedestrian detection, right? So you have images with a pedestrian and images without. That's just a two-class problem. It doesn't work that well. It works okay. You can beat records, actually. My students did this back in the, around 2010. But it's not ideal. It's much better if you train the machine to categorize lots and lots of categories. The more categories you ask it to classify, the better the representations, the more robust they are.
The more general.
The more general they are.
Yeah.
And so ultimately, why not train it to just encode the image, right? Don't try to classify. Just tell me, what are the useful, relevant pieces of information in the image that will allow you to reconstruct that image, maybe with a little loss of details, but most of the information will be encoded. So that's the idea of an autoencoder, right? You have a neural net that takes an image, produces some sort of representation of that image, and then tries to reconstruct the image from the representation. That's an autoencoder. So let's take the example of video prediction, right? So you give the machine a video clip, and you ask it what's going to happen next. And it cannot possibly predict exactly what's going to happen next, because if it's a picture of someone talking, that person can say a word or another, can move the head in one direction or the other, and the system has no way to predict what's going to happen. The example I use very often is, let's say you have a video clip where someone takes a pen and puts it on the table, and you let the pen go. The pen is going to fall, but you can't really predict in what direction. So if you train a neural net to minimize the distance between the predicted image and the image that's observed, or the frame, in the video, it cannot do a good job. It will have to predict the average of all the possible features, and that ends up being a blurry image. It's a superposition of me moving my head to the left and to the right, because it doesn't know if I'm going to move left or right. So you get blurry predictions. So one way to get around this problem is you have an extra variable that you draw randomly. It's called a latent variable. You draw it randomly, and depending on the value that you draw, it's not a single variable. It's going to be a vector, right? So depending on which values you draw, the prediction is going to change. And now the name of the game now is to train that machine to make predictions, so that as you draw different values of the latent variable, the predictions basically go through all the possible futures in the video, right? And the problem with this is that how can you tell the machine whether its prediction is good or not? To do that, you have to train a second neural net, and that neural net is trained to tell the difference between a good prediction and a bad prediction. That's called a discriminator or a critic. And generative adversarial network is the idea of training those two networks together.
I see.
Simultaneously against each other, basically.
Yeah. And when you're talking about learning representations, for example, from watching millions or hundreds of millions of videos, I asked Peter Abbeel this. Where is that knowledge, that learning stored? Is it simply in the weights of the network?
Yeah. It's in the
So
weights of
you're
the
talking about very big networks.
It could be very, very big networks.
What's the biggest network that you've worked on in this representation learning?
There's two numbers, right, in a neural net, or there is a number of different things you can, and how you can describe
the layers
it.
And the number.
One is how many layers. One is how many neurons per layer, and
Yeah.
what's the pattern of connection. And the other one is how many free parameters there are, like how many tunable parameters,
yeah.
right? Because in convolutional nets you have one parameter controls multiple connections. So, and people in natural language, for example, routinely train models that have 1 billion parameters.
Wow.
So those are pretty big networks.
Yeah.
ConvNets, many of them have a relatively small number of parameters, like it's in the tens of millions. It's amazing to say now that it's actually a small number of parameters, because if I project myself back 30 years ago, a big network had 60,000 parameters. But it could be extremely large, because sometimes you want to apply the convolutional net on a large image at high resolution, so it can detect small objects anywhere in the image. So the overall size of the network is gigantic. In fact, it's it could be tens of billions of operations, maybe hundreds of billions.
Yeah. Talking again to Peter Abbeel, he was saying yes, the learning is stored in the weights, but there are also systems to store experience in databases, so that the system can refer. In effect, it's like a memory.
Right.
Yeah.
Well, so that's actually a very interesting topic of research now for a lot of people, which is basically sort of augmenting neural nets with some sort of working memory. So if you want a neural net to do just perception, right? Perception is sort of very sort of reactive thing. You give an image, you go through a bunch of layers, and you get the answer. But a lot of tasks that we'd like machines to do involve reasoning or inference,
decision making, right?
Well, everything is decision making.
Yeah, I guess.
But several steps of reasoning, referring to past events, things like that, like having a working memory, right? Where you can hold facts and things like that. So, if I tell you a story, and in fact, this is actually kind of a scenario that people here at Facebook have built several years ago. The story is John goes to the kitchen, John picks up the milk, John goes to the den, John drops the milk. Now John goes to the kitchen, Jane goes to the den, and she picks up the milk. Then she goes to the backyard and drops the milk. Where's the milk? Okay, so you have to, or how many people are in the kitchen, right? So you can listen to a story. You can maintain a state of the world in your memory, which you have to keep somewhere, right? And then someone asks you a question, and you have to kind of answer that question. So you have to kind of figure out what's the state of the world. Whereas the milk is easy to remember because I just told you that Jane, dropped it. Right. But like how many people are in the kitchen, you have to remember that John went back to the kitchen, right?
Right.
And so there's a data set of this type that Jason Weston, Antoine Borde, and a couple others here built a few years ago called the Babi tasks, which is exactly this kind of scenario. And they invented a particular type of neural net to solve this problem called a memory network. So it's basically a neural net, a recurrent neural net.
Yeah.
And next to it is a memory. Mm-hmm. But that memory is itself a neural net. Okay, it's a special kind of neural net which is designed to kind of store data and retrieve it basically. You can think of it as a particular architecture of a neural net. And every time step, when the neural net kind of asks a question to the memory, sends a query to the memory, gets an answer back, and then as a function of the answer, adds something else to the memory and get the answer back, etc. And so now you can have a network that can do a chain of reasoning. And then people have built on this idea a lot over the last few years. The latest models that work best in natural language understanding are called transformer networks. And the transformer networks is sort of a network in which groups of neurons inside a network are basically those memory modules. And they're very similar to those memory modules. So I think there's a lot of hope that we're going to make progress in AI because of ideas of this type.
You use this this analogy several times. I don't know when you first used it. I saw it in Long Beach of the Gâteau Genoise with the unsupervised learning as the cake and the...
Yeah, you mean this?
Yes, that one.
No, you don't want this.
And the supervised as the icing and the reinforcement as the... Are there systems that you've worked on that have had this chain, or is the research still very discrete? People are working on unsupervised, or people that are working on supervised, or people on reinforcement.
So the thing that has come the closest, at least in my work, I mean, there's a lot of people at Berkeley, for example, Stanford, like Sergey Levin, Chelsea Finn, Peter Abil, to some extent,
right,
and a few other people at DeepMind at Facebook who've worked on what's called model-based reinforcement learning systems, right? And it's not a new idea. People have had this idea for a long time, where the system has kind of a predictive model of the world, which allows it to predict, for example, if I'm driving a car, I'm next to a cliff, and I turn the wheel to the right, I'm going to run off a cliff, and nothing good is going to happen, right? I don't need to actually try. I know I have a model of the physics in my head that tells me this is bad. And so there's quite a lot of activity now on model-based reinforcement learning, and it didn't happen too much in the past for the same reason that people resisted using deep learning for a long time, which is that the theory doesn't work. So the theory tells you, there's a proof that model-free reinforcement learning will converge in certain conditions, right? There's no such proof for model-based. And experimentally, if you don't do it right, model-based reinforcement learning learns faster, but it doesn't work as well as model-free. And so that caused people in the mid-90s, at the same time that people abandoned neural nets for simpler models, they also abandoned model-based reinforcement learning for model-free. And there's this joke about, like, it's a popular joke in France, the French like mathematics, right? And the joke is, it works in practice, but does it actually work in theory? And the whole community essentially had this attitude that it works in practice, but we don't understand why, and we don't think we have good theoretical ways to understand why, so we're just not going to work on it anymore. In my opinion, this is looking for your lost car keys under the street light, even though you lost it someplace else. So another joke. So this model-based reinforcement learning, I think, is becoming really interesting, particularly for people who work on robotics, because it's very hard to train a robotic system in simulation for things like grasping, because simulators are not very good. So there's a lot of interest. My own work, I try to stay away from reinforcement learning. Because I like the efficiency of gradient-based learning, and reinforcement learning, basically, you can't use gradients because you can't estimate the gradient of the objective function. You can estimate it, but you can't compute it directly. So I've done things like our latest paper at iClear just a month ago was about the idea of training a predictive model of what cars around you are going to do. So you can run this model for several steps, maybe several seconds, and it will predict what the cars around you are going to do. And of course, you can't exactly predict, so there is some variable you can draw, and it will predict multiple futures. There's a cost function you can compute, which is how far you are from the other cars, whether they're going to bump into you, whether you are in your lane or not, whether you are going at the speed you want, various costs like this. And what you can do is train a neural net to produce the best steering policy and braking accelerating policy, so as to minimize the likelihood of collision by just minimizing this cost. And so you're using this model to predict what the future is going to do. You have a cost function that's differentiable, and you just train a neural net to optimize this objective. There's no reinforcement learning. It does the same thing that a lot of people try to do with reinforcement learning. But because the cost function is differentiable, there's no need for reinforcement learning.
There's certainly generalization going on, but it's generalization that's fairly narrow. I mean, because it's generalization within one data set.
That's right.
You have the training data, then you pull out a test data, and it generalizes from the training to the test data. But if you use a different data set, it usually doesn't work. So that's one question is how do you get to that generalization? And then the other question is there real transfer learning going on anywhere where the learning that's stored in the weights can actually be applied to a new problem?
Well, so, transfer learning works, right? So if you have a big data set, regardless of what the task is, for image recognition, you pre-train on this data set and then you fine-tune on whatever data you have, which may be smaller, right? So this kind of stuff works. You still need data for the second problem. One thing that people are trying to do is sort of multitask learning. So you train a neural net on multiple data sets, and you hope to get some sort of more generic image recognizer or whatever it is. And then it's easier to specialize it for a particular task because it's learned already a lot of different tasks. So that's one thing that Facebook has been doing, for example, where you take, 4 billion images from Instagram, where people, when they post a picture on Instagram, they put hashtags.
Right.
And so what the Facebook people did was select the 17,000 most frequent hashtags that correspond to actual objects, physical concepts, and then train a neural net on those 4 billion images to predict which of the 17,000 hashtags are present. And it does a pretty terrible job at it, but it learns to represent images in such a way that it can do that prediction as well as it can. Then you chop off the last layer and you fine-tune the network on ImageNet, Coco, whatever task that you're interested in. And you can beat records this way. This was a paper published last year. And so that's a sort of edging towards kind of almost unsupervised learning in the sense that the data is not carefully curated. It's just whatever people type for hashtags. But ultimately what you want to do is self-supervised learning. So, I'm not giving you hashtags. I'm just, here are pictures. You can have as many billions as you want. Encode pictures in such a way that the features that would be elaborated by the system then would be useful for any task, any vision task that you can imagine. That's the challenge really of self-supervised learning.
Ultimately, the goal is to knit together all these different techniques and strategies into general artificial intelligence. Is that something that you stay away from, or do you have an opinion about?
Okay, well, I have a lot of opinion on this, yes. Yeah. Okay, first of all, I don't like the term AGI, artificial general intelligence.
I've been corrected on that point before.
Because human intelligence is actually very specialized. We like to think of ourselves as being general intelligent. We're not. We're very specialized machines. So AGI is a misnomer. Human level intelligence, that's a better question to ask. So, could we build machines at some point that will be as intelligent as humans in all the tasks that humans are intelligent in? And the answer is, of course, there's no question. It's a matter of time. And it's very important to make progress in that direction because we'd like to have machines that have some level of common sense. Because we'd like to be able to build, virtual assistants that help people in their daily lives, can answer any question you have, can kind of manage your interaction with the digital world and with each other. So that, that would be kind of transformative in terms of technology that's available. We'd like image recognition systems that don't get easily fooled with like self-driving cars that are very robust and that understand how the world works enough that they make the right decisions when they see unusual situations. So that's a really important question for practical reasons. And then the question is, how is it that the best of our AI systems have less common sense than a house cat, or actually a rat, Washington Square Park rat. Yeah. There is something that animals, some learning process that animals have access to acquire all the knowledge they have about the world that we don't have in our machines. So one hypothesis, or my money is on things like self-supervised learning, but there might be other favorite approaches from other people. So it's a very important problem to solve for machines to learn by observation, learn without requiring too many label samples, perhaps accumulate enough background knowledge by observation that some sort of common sense will emerge. And we'll have, not just intelligent virtual assistants, we'll have dexterous robots, the household robots that everybody has been dreaming of, right? We don't have the technology today.
Right.
So, yeah, that's a, very, very intriguing question. There's a lot of people at Facebook working on
a question, but one that you're optimistic can be answered.
There's no question that can be answered. It's a matter of how much, how long is it going to take and how is it going to be done.
That's it for this week's podcast. I want to thank Jan for his generosity. For those of you who want to see a video of this interview, visit our website at i-on.ai. You can also go into greater depth about the things we talked about today by downloading a transcript of this show from the site. I've inserted links into the transcript to make it easier to follow some of the things that Jan talked about. We've been getting good feedback from listeners, and I hope to hear from more of you. You could help a lot by rating and reviewing the podcast on whatever platform you use. The ratings and reviews help surface the podcast for other listeners. Let us know whether you find the podcast interesting or useful and whether you have any suggestions about how we can improve. The singularity may not be near, but AI is about to change your world. So pay attention.
No, I can't get close till I buy my time.